Okay, let's get down to some calculations and very basic statistics. So all of you, belong to, banking. So I'm sure you must be looking at the numbers, the data day in, day out. In statistics, so Six Sigma uh, use extensive statistics, but simple and easy to understand statistics, something that we would have studied in our school days. So the statistics that we use is pretty simple, very, very basic. And, that is what we will understand now. So I hope you're able to see the project charter slide. Remember, we in the beginning we talked about Six Sigma is all about converting the business problem into a statistical problem, then finding a statistical solution, and then from there converting the statistical solution back to a practical solution. How we do that is by looking at the data and working with the data. So any data analysis that we do, any data in the world can be looked at it. We can look at it from two perspectives. One is, where is my data centered? What is the measure of central tendency of the data? What is that one value that represents the entire data set? And then the second area is the measure of dispersion. So we'll talk about measure of dispersion later on. Let's come back to measure of central tendency. So quite often, more often than not, when we are generally asked to represent the data, it is said that, on an average, how much is the per capita income of that country, or how much is the performance on an average. We use average a lot, right? We do it more or less every time whenever we represent. So when we talk about the average of a data, what essentially are we saying? We are saying that what is that one data point which is representing the entire data set, the entire population. So essentially, when we're talking about centering, we are talking about a data point that represent the entire population. Okay, so there are three ways to measure a central tendency. One is the average, or it is also called the mean, median, and mode. There are three ways to represent the central tendency of a data. Now, this topic is very important because hereafter, everything that we do in Six Sigma would be primarily on statistics, and we'll do a lot of statistical testing. So, just ask me any question that you have, and it is a very basic concept. So, if this is clear, and it definitely would be, but we would understand and we would learn how do we convert the business problem into a statistical problem right here when we are looking at the data analysis. Okay, so I was talking about the measure of central tendency. So in a way, that is one value. Where is my data centered? Which is that one value that represents the entire data set? And it is calculated. There are three ways of calculating it. It is the mean, median, and mode. How do we calculate mean? We all know that sum of everything divided by the count. How do we calculate median? So median is the middle point of the data set. To get to the middle point, you would need to either arrange it in the ascending or the descending order and take the middle value, the middlemost value. If the total number of data points are odd numbers, then take the number appearing in exactly in the middle of the series. If the total number are even, then you need to take average of the two middle numbers. Okay, and the third one is a mode. Mode is the most frequently occurring number in a data set. Now let's look at an example and let's calculate mean and median, and let's see, what is the difference between that. And let's take up a scenario and calculate that. So what happened? Sometime back there was a study done in London. So there was one of the postcode in London, and the government said that we want to, study the living standard of people living in that particular locality. So they picked up a postcode X, Y, 1, 2, 87 something HJ. Yeah, that's a hypothetical postcode. And what they started to capture, they collected data on um, the monthly household income of the people living in this particular postcode. Okay, so they went to household A, B, C, sorry, C, D, E, F, G, H. Okay, so they went to these household. For the ease of calculation, will only take 7. Monthly income. Okay, a household A, when they captured the data, they found that they're earning 2,000 pounds. Household B, about 1,800. Household C, about 2,200. About 21, 19, 2,000. Let's say 2,000. Okay, this was the monthly household income of the people living in London and this particular locality. Okay, now data went back to the government, and the reason government was doing this particular study of the living standard is that government wanted to take a decision whether they would want to give subsidies or they would want to impose taxes on people living in a particular locality. They wanted to take the taxes from people living in a particular postcode, high income group, and give it to a low income group. So they were trying to play the Robin Hood there. So they collected the data, and as we always calculate, they calculated average or the mean. And average came out to be 2,000 pounds. So 2,000 pound, London, not a very high income group. So government said that, okay, let us start giving subsidies to people living in this particular locality. So subsidies it is. People were happy, everything was going on fine. Okay. Now what happened after 1 year, or rather it happened for a couple of years, and then they said, okay, it's been about 2 years, do the study once again. So they again started collecting the data. So again, household A, it went to 21, it got dropped, this got dropped, it got increased, this became 2000, this became 1900. Something changed in this particular household. What happened is, so let me just change the example. Let's take up a real-time current example. So, Jeff Benzo, he purchased a house in this particular locality. Okay, so and they were calculating the monthly household income for Jeff. Right. So because now see what has happened, because of this one Jeff here, one individual here, is changed the entire equation. Now, when they again collected the data, they said, the people living in this particular household, they are, they're earning somewhere about 144,000 pounds a month, right? And we have been giving subsidies, so they canceled the subsidy and they started imposing the taxes. Okay. Now, so what happened is because of one individual, the entire equation has changed. So this is what average does. Because average tend to get impacted or highly influenced by the too high or the too low or the extreme values. Do you think average was the right measure in this kind of scenario? See, here we
No.
can see it's only 7 data points, right? So and there's an extreme data point. Let's say if it would have been 3,000 as well, it would have not increased the average income that much, right? But imagine instead of 7 data points, had it been 7,000 or 70,000 or 700,000 data points, you would have not been able to identify the extreme value, right? So that's the reason why looking at average alone, is very dangerous. Now, here in this kind of scenario, we can use another measure of central tendency, which is median. So median is highest minus lowest, and in Excel you can just put the formula and it will calculate the median. So in spite of Jeff being there in that, still the median is coming out to be very close to reality.
Mm-hmm.
And so what that means is, and when it was 2000, it was exactly equal to mean. Okay, so median doesn't get impacted or doesn't get influenced by the extreme value. Okay, so always median is a better measure than average. Looking at average alone is bad. But unfortunately, in statistics, we don't have too many studies which are median based. Everything, almost 90% of analysis and studies are average based. That's the reason why measure of centering has to be looked upon, has to be always looked along with measure of dispersion. Okay, you understood the measure of centering, measure of central tendency.
Yep.
Okay, so when we do our daily analysis as well, we should, when we calculate average, we should, parallelly, we should also calculate median as well to see, is there a significant difference between median and average? If there is, then you doubt the data. There's something wrong with the data, right? There are some extreme values which are impacting on the measure of central tendency. And the third one is mode. Mode is the most frequently occurring data set. So 2000 is occurring twice here. 21 is also occurring twice. So, it is a multimodal. So we take 2000 here. So as a part of Lean Six Sigma green belt, black belt, till black belt level, we only deal with average and median. We don't do too much studies on mode. So we'll keep mode out of the equation right now. We'll only look at the mean and median. Okay, so when we look at the data, the first thing that we need to look at is what is the measure of central tendency. And when we're looking at the central tendency, there are three measures: mean, median, and mode. Okay, if there are extreme values in the data set, then the mean will get impacted. So when we have a data set which has extreme values, it is always better to look at the median. Now, this is measure of central tendency, which tells us where is my data centered. Now, there is another measure that we talked about, which is measure of dispersion. Measure of dispersion means how dispersed my data is, how distributed my data is. So there are three measures for a dispersion. One is standard deviation, then we have variance, then we have range. Okay, now before we go ahead and do that, let me just ask you a quick question. It's a scenario. There is a group of students who went for an adventure picnic in a jungle. While they were traveling, they came across a river that they needed to cross on foot. We have been given average. The average depth of the river was 4 feet. Imagine you are among the student. Would you cross the river on foot? So, average doesn't give us the complete story. right? So there's always a danger, in the average. So it might be something like this: 1.5 feet, but 18 feet here and then 2 feet here. Average would still be about 4 feet, right? So when I was getting my first training, my trainer told me like average is like my one hand is in the oven and the other one in the refrigerator, in the chiller. So on an average, I'm doing fine, right? So that is what average is. So there are organizations who conduct training for the entire 1 or 2 days only to put this point across that average shouldn't be looked alone. Average is bad. But everything, including the GDP and everything of the country, is calculated in average. But then nowadays, you would have realized there's a lot of talk on median is, there's a lot of talk on medians. People have actually started projecting the median as well. But looking at average alone is bad. But then if you club it with a measure of dispersion, you can actually get meaningful representation, meaningful interpretation out of the data. So what is measure of dispersion? How distributed, how spread my data is. So as we mentioned, there are three measures: standard, deviation, variation, and the range. Okay, let's look at what standard deviation is. Now, can do you remember the formula for standard deviation? What exactly standard deviation is? So not the formula, but the concept behind standard deviation. So let's look at a data set. So here is a data set that we have, which is for claim processing cycle time. This is a data set for claim processing cycle time in minutes. So first claim is processed in 34 minutes, second in 30, third in 25, fourth in 19 minutes, so on and so forth. This is for a healthcare service provider. Uh, so and this cycle time is X, right? So how we calculate standard deviation, and the concept behind standard deviation is that it calculates the sum of square of distance of each and every data point from its mean. So to calculate standard deviation, we need to calculate mean. So let's calculate mean for this data set. I mean, there's a simple formula to calculate standard deviation. You type standard dev and it will calculate standard deviation. But we're just trying to understand what is the concept behind it. So we got the average, which is 33. So we do x minus x bar. X bar is the value for mean, which is this, minus this value. So this is the distance of each data point in the data set from its mean. Now, so you see there are some negative values here as well. Now, because it is, so mean is the middle value, right, of the data set. So it will have equal number of values or equal amount, equal value above and below it. So if we calculate distance of each and every value from the mean, the sum of everything should always be 0. Right? Okay, but there are certain negative values here. So if we do the sum, it has come to be 0, because obviously because it's distance of each value from its mean. Now, if you actually look at it, there are certain negative values. To negate the effect of negative value, we square these values. So I've just squared all the values and we got this. Okay, so the standard deviation is the sum of squared distance of each value from its mean. So if the mean is in the middle, it is calculating the distance of the next data point, sum of square of the distance of the next data points. So if you look at this particular concept, so tell me one thing: is standard deviation, higher standard deviation better or a lower standard deviation better? So what we are saying, standard deviation is actually the distance of each and every data point in the series from the center point or the mean value. Is lower value of standard deviation better, or is higher value of standard deviation better? If my first claim is taking, let's say, 34 minutes, I know the next claim, depending on the standard deviation that I have, it's going to take somewhere about around this time only. But if my standard deviation is high, my first claim can take 34 minutes, my next claim can take 80 minutes. Okay, so if standard deviation is high, that means there's a lot of variability on the process. That means process is not consistent. So I would not be able to predict the process and devise any solution for that particular process because I don't know what's going to happen next. So this is standard deviation. That's a formula. That becomes a numerator, and the denominator is n minus 1. If you're doing it for a sample, it is 9 under root of this, square root of this becomes standard deviation. Okay, right. So standard deviation is 9.9.43. What that means is, there can be variation of 9.43 in the every time we are processing a new claim. If the process standard deviation is 9.43, if and within the mean. So if you remember, we discussed or we talked about the statistical concept of Six Sigma, which said it is the number of standard deviations you are able to fit between the mean and the specification limit given to you by the customer. So the mean of the process, if it is let's say 30, and let's say the standard deviation of the process comes to 10. So, and the customer has given you 40 as a target, 40 minutes of processing time. So that means you would only be able to fit say one standard deviation. So one standard deviation becomes the capability of the process. So that means your process is functioning at 1 sigma level. And this is something, I'll show you graphically as well. So this is how you would calculate standard deviation. And another way of calculating is you simply put the formula STD. You're doing it for sample. So standard stdev.s. You select everything and it gives you 9.43. And it's the same as we calculated. Okay, so that is standard deviation. Variance is square of standard deviation. So if you square the standard deviation, you will get the variance value, sorry. Once again, I'm just going back to presentation. So standard deviation, variation, and range. You know how to calculate range? It's maximum minus minimum, right? Or the highest minus the lowest value, right? So that's range. So whenever we look at the data, we look at it from two angles. What is the measure of central tendency and what is the measure of dispersion? Okay, and then basis that we try to ascertain what is the problem in the process. Is it a problem with centering or is a problem with dispersion of the process? So with that, I'll just move ahead and let me just talk to you about one of the scenario, and let's see uh, the understanding. So the scenario is that post attending this training, we go back, to a workplace, and we've been asked to travel on a Six Sigma assignment to a different country altogether. Now there has been increase in the airplane crashes in the recent past, so we are a bit hesitant, and we have studied Greenbelt as well. So we wanted to look at data and we wanted to analyze the data as well. So after much convincing, airline agrees to share the landing performance of the pilots with us. We need to decide which pilot do we want to fly with. Now there are two pilots. We have pilot A and pilot B. The diagram in gray is the airstrip where the plane would land, and the area within the blue lines are the safe landing zone. And the asterisks that you see, these are the individual landings. Uh, we have exactly the same number of landings for pilot A and pilot B. So now, you have the historical data of the plane landing and the plotted the same to look at it visually. And this yellow dot, as I mentioned, these are the safe landing zone. Within the safe landing zone are the occurrences of the plane landing historically. Good news is that both the pilots have never crashed and have always landed in the safe landing zone. Okay, so that is the good news. Which pilot would you want to fly with? See, if you calculate the average for both the pilots, it will be exactly at the same point. So if I calculate the average, it will probably come somewhere over here. Yeah, here it is. If I take the average, it will probably be somewhere over here for both the pilots. Okay, so if the airlines would have given us the average data, we would have not been able to, analyze anything at all. So, the idea is, and as sorry, as you mentioned that because pilot B is more consistent. If you look at pilot A, is all over the place. He has never crashed, but you don't know what he's going to do next, right? Even if he goes 1 inch here or there, probably 1 meter, I don't know, whatever, uh, the plane would crash. Pilot B, he's always, his landing has been, there's very little standard deviation between his landings. Even if he defaulted in his normal process, from his normal process, right? So let's say next landing, instead of here, let's say instead of this dot, he defaulted and he landed here. So this one is a default landing from his normal process. He normally doesn't do that, but he commits a defect, still it will be within the safe landing zone. There's a lot of leeway of committing the defect. Okay, so because he has made the process so robust, even if he goes beyond the normal behavior of the process, still it will not be a defect for the customer, which is you, who's flying in the in his plane. Wherein pilot A, he's over the place. The moment he goes little beyond, boom, the plane crashes. There is no consistency whatsoever. As a customer, you would always you would always see the consistency. You would not be bothered on the average. So whatever it is, you would always be bothered more on the consistency, because consistency is what you would experience, or the standard deviation is what you would experience. This is exactly what is the scenario with the Six Sigma processes. So let's understand, what exactly is a Six Sigma um, process, and why we say Six Sigma, and how do we calculate Six Sigma and all that stuff. So let me just try to draw something for you. So let's say this is a process. Let me just increase the width a bit. Okay, so this is the process. Uh, you uh, you understand the specification limits? What exactly is specification limit? So specification limit is a target given to us by the customer. For example, you talked about paying payment to the vendor, and let's say there is a SLA defined which says that you need to pay within 9 days. Okay, so 9 days, 1 to 9 days is the time that you have to make the payment. Okay, so 9 days is a specification given to you, by the business or by the customer. So specification can be of two types. So it can be upper specification limit, or it can be a lower specification limit. Upper or lower. So when you say, you need to pay the invoice within 9 days, it is the upper specification limit. So the moment you go above 9, there is a defect that is created. You with me? For upper specification limit?
Yep.
Can you give me an example for lower specification limit? Yeah, so it can be, anything, but an example of the lower specification limit, target on the lower side given to you by the customer or by the process. So let me just give you an example. Let's say, Six Sigma green belt exam, and I'm saying the passing marks is equal to 70%. So it'll never be equal to, it'll be, greater than 70%. Okay, so this is the lower specification limit. The moment it is less than 70, there's a defect that is created. So there can be a scenario where it can be only the upper specification limit, or it can be the lower specification limit, or there can be both sided specification, lower as well as upper specification limit. Okay, so let's say we have a process, and then let's say this is the middle line, which is the mean of the process. And let's say we are trying to, so give me any scenario and let's calculate. Let's try to see, what is the sigma level there. So let's take up a scenario of a call. You're calling up a call center, and let's say 30 minutes is the average time for that particular call. Average handling time for that particular call. Okay. So for any, in fact, we'll have to change the example. I'm just trying to show you something which has an upper specification as well as lower specification limit. So let's take an example of a bottling plant, and Coke bottling plant. And what we are saying is, so 300 ml should be the the amount of Coke that should be there in a bottle. Customer has given a specification that if it is more than 310 ml, customer would reject. So customer for the bottling plant is Coke, and then less than 290 ml, the customer would reject. So 290 is a lower specification limit. Yeah, you with me? And then 310 is the upper specification limit. So it is LSL, lower specification, and this is USL. 300 is the average. Okay, let's say we collected the data, and what we found out that the standard deviation of this data set, it is let's say it is 5. Okay, so standard deviation is 5 ml. So what we are saying is that on an average it is 300 ml, but then how many standard deviations can I fit between the average, which is 300, and the specification limit or the nearest specification limit? Here both the specifications are at equal distance. So if we look at it, what we are saying is that we can fit 2 standard deviations. So from 300 to 310, it is 1 and 2. You with me so far? Am I able to explain till now?
Nope, that's good.
Okay. All right. So plus 1 standard deviation would mean 305, and 2 would mean 310. 10. Same thing on the lower side, minus 1 standard deviation,
295.
295, and minus 2 would mean 290 ml. So what we are saying here is that this process between the mean and the nearest specification limit, I can fit 2 standard deviations because that is the standard deviation of the process. Okay, so that means this process is working at 2 sigma level. Anything outside this is a defect. So let me just try to draw something here. So just give me a second. Let me just try to explore if it gives me a feature to. Oh yes, I have the drawing tool. So the process looks something like this. The distribution would look something like this. Okay, it will also continue. This will also continue. So the area here that we are, area that we are talking outside this area and this area, anything produced here is a defect. Okay. Now, if we, so just give me a moment. Let me just try to find out how do I erase this thing. Okay. Anyways, so this is a defect, right? Now, considering the same thing, so if I look at the same thing and again presented this slide. Okay, so so this is for 5 ml of standard deviation. Now let's say we work on the process, and we would have reduced the standard deviation, let's say down to 2.5 ml. So what would happen now is that instead of 2 standard deviation, I would be able to fit more than 2 standard deviation. Rather, I would be able to fit 4 standard deviation between the mean and the nearest specification limit. So what's going to happen is plus 1 standard deviation is going to be 302.5, 302.5 plus 2 standard deviation is going to be 305, then plus 3,
307.5.
307.5, and then plus 4, 310.5. Right, same would be the case on the minus side. Minus 1 is going to be, it's going to be like this. So what is happening now? I would be able, because I've reduced my standard deviation, I've reduced the spread of the process, I've made it much more consistent. I'm now able to fit 4 standard deviation between the mean and the specification limit. So now I'm able to fit 4 standard deviation between the mean and the specification limit. So now my process spread would look something like this. So what has happened in earlier in this process? What is the difference? This area has reduced. So that means I am committing less defects now. Okay. Let's say we again worked on the process and instead of 2.5 ml, we made it, we reduced it down to 1 ml. So what is happening now? I am able to fit 10 standard deviation between the mean and the specification limit. 10 standard deviations. Okay. So my graph would look something like this. Same graph. It'll look something like this. So what has happened now? I've made the process so robust that this is the normal behavior of the process. Even if I commit a defect and the next data point comes here, which is outside the normal behavior of my process, but still it will be within the upper specification and the mean between this particular period, this particular range. The more I am able to shrink the process, the lesser is going to be the standard deviation. Rather, the lesser I make the standard deviation, the more my overall spread would be near to mean and within the upper and lower specification limit. So this is the entire concept of, there's the overall concept of Six Sigma. If you understood this and if you are able to do this, that's it. Nothing else to be done. This is what Six Sigma is all about. If you compare it with the same example that we took earlier, it is exactly the same scenario as pilot B. The pilot B standard deviation is so low, even if there is a default which is outside the normal behavior, still it is not a defect for the process. Same was for the other scenario. And this is how we calculate as well. So the simple formula to calculate Six Sigma is upper specification minus or specification minus mean divided by standard deviation. So in a way, what it is saying, how many standard deviations can you fit between the nearest specification and the mean? The value that you have is the sigma value. Value that you will get would be the sigma value. Okay, now with that, what we have done is we have identified a few areas, and so if we are able to establish, there might be certain process where the problem might be with the centering of the process. There might be certain processes where the problem might be the dispersion of the process. So depends on what is the voice of the process, we would take the action. So business problem, we had the Six Sigma, the product Y. We would convert it into a statistical problem. How? We will look at the measure of central tendency, measure of dispersion, and we would try to ascertain, what is it that we need to work on? Do we need to work on the centering of the process? Is the centering an issue, or is the dispersion an issue in the process? If it's a dispersion, then we work on the standard deviation, variance, or range. If the problem is with the centering, we would work at mean or median. Okay, so this is what the entire concept of Six Sigma is all about. Let me just quickly show you something. See, this is what happens. If your process is working at a 2 sigma level, the one on the extreme left hand side, there would be areas which is beyond the upper and lower specification limit. You make the process much more robust. You brought it down to 3 sigma level or increased it to 3 sigma level. Then, there are less number of data points outside the specification limits. You made it much more robust, 4 sigma. Again, there is more leeway for the defect creation. Then you made it better. It is 5, 6. So if you look at it, 6 sigma, it is becoming very, very close to mean or the average. So even if there is a defect, it will not be a defect for the process. Just so based on that, based on this explanation of Six Sigma, if you are able to understand what is it that you need to target, 50% of the job is done. So let me just give you some example. Six Sigma project target, and visually we have depicted the process. Here it's a bullseye. So there are 3 scenarios. Scenario A, B, and C. Let me just go round robin and ask you, what do you think is the problem? What should be the target of your Six Sigma project? So let's look at scenario A, and why. So Charles, why don't you go ahead and attempt? What do you think is problem? What would be the target of your Six Sigma project? Would it be shifting the mean or reduction of variation? So target is this, that yellow bullseye right at the center. The red dots, or the red symbols, every time you try to hit this, this is where you land. If your project is something like this, after you've collected the data, what do you think you would do?
Wait, so which question are you asking? Are you asking if if a project of mine fits one of these scenarios, or if we're in each distinct scenario, what would be the
Now,
steps in order to get it
yeah,
toward the center?
not the steps, but if you're in scenario 1, what will be the target of your project? Would it be shifting the mean, or would it be reduction of variation?
Oh, reducing the variation.
reducing the variation. It's the perfect example. It's the same example of that airplane that we saw. If you are able to reduce the variation, it'll come exactly at the center. Absolutely right. Thanks. Scenario B. Brittany, what do you think you would do as a Six Sigma project lead? Would you shift the mean? Would you reduce the variation?
I think for this one, you would shift the mean since it looks like it's all kind of gathered in one area.
Mm-hmm. Yes, it is very precise, but it is off target, right?
Mm-hmm.
So you pick it up from here and keep it right in the middle, and you're done. Nerlin, how about you? Scenario C.
I think scenario C is already on target. It's probably already working lean. I don't think you could make it work any leaner.
Right. Now, there's always scope for improvement, but then it really depends. If it's business sense, then you improve. But then you are right. Absolutely. Scenario C is the ideal process. If we would have, like Brittany said, if you shift the mean and bring it in the middle, you will have a scenario C. So this is all there is in Six Sigma projects. So if you get a project like scenario B, you just pick it up and place it in the middle, and you're done. That's it. I wish it would have been that easy, but that is what we need to do. But then to do that, we need to take a series of steps. Okay, so 50% you're done. You understood the concept of Six Sigma. Statistically, how would you calculate? What is it that you would look at, and what is the how would you convert your business problem to a statistical problem? Let's do a quick recap and see what we have done so far, and then we will try to tie in everything together. When we initiated, when we started the discussion, or rather when we would have started the Six Sigma project, the first thing that we would look at is we will go to the customer, we would collect the VOC, and then we would take that VOC, we would convert it into a CTQ, right? So CTQ is critical to quality element, something which is measurable. And then we would after we have the CTQ, and there are various things that we can do. We can use the CTQ tree, we can use the other things, we can use the quality functional deployment, and various other we can use the Kano model, etc. And basis that we will be able to identify what exactly is the CTQ or the project Y that we want to target, that we want to improve. Then we will put together the define phase, and in the define phase, the first thing that we do is to create the project charter. So in the project charter, we would mention the business case, the problem statement, the goal statement, the project team, the milestone, etc. And then after we have the project charter prepared, we would put together the SIPOC of the project. So with the supplier, input, process, output, and customer, here the process map is going to be a pretty high level. So that is where the define phase ends. So the output of define phase, you would have an identified CTQ, a project Y, a problem statement, goal statement, project charter, and the tools that you would have used as VOC to CTQ, QFD, project charter, and SIPOC. So this is what define phase is all about. Any questions on define? Okay, are you able to see the screen, which is see the slide which is define performance standard, right?
Yeah.
Yep.
Okay. So performance standard, if you look at it in measure phase, what we do is that we take care of three things. One is what to measure, how to measure, and how to ensure what we are measuring is correct or not. So performance standard is a requirement, or it's a specification imposed by the customer on a specified or a specific CTQ. It gives us, or it answers questions about what does the customer want, what is a good product, or what is a good process, what is a good service, what is a defect. Some of the examples of performance standard in terms of timeliness or accuracy can be on time receipt of payment, accurate and complete information. And this performance standard is the one which helps us to translate VOC, voice of customer, to the voice of the process. The intention is to convert VOC into measurable characteristic, and we would need to, for this, we would need to clearly define the operational definition, the target, the specification limit, the defect definition. So operational definition, what is an operational definition? It is a precise description of that tells you how to get a value for the characteristics that you're trying to measure. So when I say value for the characteristics, so basically it defines the CTQ in English. What exactly are you trying to measure? And it is important to put together the operational definition, because you might have a project and you might have a project team which is working across geographical location. You might not be present in the same location, and it is important for everyone to understand the exact operational definition of the project why that you're trying to improve, and also on the access on which you are trying to collect the data. So the operational definition should include what is it that you're trying to measure, and it should clearly define everything very clear. There should not be any ambiguity anyone might have in terms of the performance standard, and we need to bring everyone onto a common understanding. So the performance standard or the operational definition, it will provide a clear way to measure. Wherever possible, you document the formula for calculation as well. So it should essentially tell what is it that you're measuring, how is it that you're going to be measuring, and what are the results that people can expect. So for example, and operational definition can be tricky. So for example, if you calculate utilization, and if we only talk about the utilization, different individuals would have a separate way, different ways of measuring it. So once you define what and how to measure, you take out the probability of making mistake in terms of it calculation. So good operational definition can be utilization would include all the production hour, including the overtime hour incurred on the client projects. It would include, so you list down whatever it includes. It includes the core audit work, the project specific calls, the training on the client specific audit requirement, time spent with the auditors, etc. And then you can also mention what you would exclude. So you can exclude probably a manager hour on production or on training would be excluded out of the utilization. So it's very important to also wherever possible, as I mentioned, list down the formula for calculation as well. So also you need to define the specification. By specification, we talked about the upper specification and the lower specification limit. You would need to clearly define if it is both sided, the process that you're trying to improve, the process standard, if it is both sided specification, or if it is only one sided, single sided specification. And you would also need to list down, what is the, tolerance limit in some of the projects. So there might be a specification and there might be a separate tolerance limit as well, which might be some percentage above the specification limit. So you would need to ascertain that and document that very, very clearly. Okay. So in a nutshell, the performance, the operational definition, it's a precise documentation or precise description that tells you how to get value for the characteristics that you're trying to measure. Okay, and wherever possible, you be as elaborative as possible while putting together the operational definition. Okay, so with that, we'll move on to another aspect of data. Any data that we have, it can be broadly categorized into two types. And these two types are continuous data and discrete or attribute data. So what is continuous data? Continuous data is a data which can be measured on a continuum or a scale. It is something that can be broken down into smaller parts and would still have the same meaning. For example, money. Within money, the amount of money, let's say money in million, it can be broken down into thousands, which can be further broken down into 100. Still, the meaning would not change. We are still talking about money and the amount of money. Okay, so that is a continuous data. Another example can be the time. Time can be in hours. Hours can be broken down into minutes, and we are still talking about the time. We can talk about the volume or the size. All these are continuous data. So in other words, we can say continuous data is a data which characterizes a product or a process feature in terms of its size, weight, volt, time, currency, etc. Is a measurement scale that can be meaningfully divided into finer increments of finer increments or finer increments of precision. Wherever possible, we use continuous data because there are more powerful statistical tools available for interpreting continuous data. So it is generally, that is the reason why we generally prefer it over the discrete data set. Now, on the other hand, what is discrete data? It is the information that can be categorized into classification. Generally, it is going to be counts, and only a finite number of values are possible. It cannot be broken down into finer refinements. So anything which is not continuous would be discrete data. So discrete is also called the attribute data, and continuous is also called a variable data. Example of discrete can be the number of part damaged in a shipment, all type of data which are which have categories, qualitative or categorical data. All these are example of discrete data. Let's do a quick exercise. Let's pick up two continuous data and two discrete data from wherever we are or from our own respective process. Okay, so let me start with you, Charles. Two continuous and two discrete data, either from where you are, your surroundings or your work area.
So what do you like?
Any two examples of continuous data and two examples of discrete data. So it can be your surroundings, it can be your process, work area, anything.
Okay. Oh, if you're just talking about just like say, so something that's like discrete count, like something like a count would be maybe just like a number of projects in a particular group.
Right.
And to break it down further than that, because projects here are listed in tiers, so it could be just like the number of projects in a particular tier. So it could be something that's more wide-ranging,
Absolutely.
or something that's just a little bit more in depth. But yeah, just a count of overall projects or a count of specific tiers of projects, something like that.
Right.
Variable, let's see. Well, then something like a variable could be then certain budgets within projects, because that over time that can change.
Project within project, how would you define that? You would have to talk about the count of project within the project. So when you start talking about the count, it becomes a discrete data.
No, not in terms of account, but like say for example, like Like if I take a project for, let's say $1 million or something like that, it's never going to really stay. It's never, yeah, value. It's pretty much
Value
never
of the
going to,
project, yes.
it's never really going to stay that amount because it changes over time depending on how much work is being done or work that isn't going to be done after all. Timelines could
Right.
change. So things like that change all the
Right.
time. So that thing
Right.
that you
So
started out
if you're
with.
talking, right, absolutely. So if you're talking about the value of the project, I agree, it is a continuous data. But then the definition that the value is going to change from project to project, that will not be the correct definition to interpret whether it is a continuous or not. Because see, if let's say you're doing a project, let's say you want to do an improvement project and you want to pick up, I want to increase the value of the project that the organization is doing. Right. So, so that value, the project Y becomes the value of the project. Right. So that value probably in $1 million, you can convert it down to $1,000. 1,000 can be $100, but still you're talking about that value of that particular project. Right. So it is a continuous data for sure, but you're talking about the same thing. Right. So that is also important.
Okay.
So another example from continuous data, for continuous data, sorry.
I don't know. I can't think of anything at the moment.
Okay, no problem. I'll come back to you. Just think about another one. Brittany, how about you? Example of continuous to discrete. So anything that Charles has covered, you cannot say that now.
Okay.
And by the way, the value of the product is gone because Charles already mentioned that. So you still need to give me two continuous.
Okay.
Okay, so you just think about it. Let me just go over to Nerlin. Nerlin, two continuous, two discrete from your side.
Discrete data could be the amount of lights that I have on and versus the amount of lights I have off in my house.
Okay.
Continuous
Versus,
data could be the energy being used.
Absolutely. Okay.
And the amount of money being spent from the energy used.
Okay. Is that continuous or discrete?
That would be discrete.
No,
the value, money, right?
No, the amount of money that you're spending would always be continuous. See,
continuous? Okay.
Whenever there's amount of money is always it should be continuous.
Okay.
Okay. Discrete. Another one. So I'll give you an example. Number of slides that we have in the presentation. Number with this count, that is discrete. Okay, so it can be any number.
Number of people working in a building.
Absolutely, that's discrete. Okay, I'll tell you the reason why we're doing this particular exercise. It's very important exercise because generally in a Six Sigma project, what we prefer is to pick up continuous project Y. And the reason why we want to pick up continuous project Y is because there are more statistical tools available for continuous data as compared to discrete data. Continuous data will show most information about the variation in the process, whereas discrete data will not show any information about the variation. It can only give us a count, number of defects, that's it. So do remember, data type is critical, and all the statistical tests hereafter will differ depending on the data type. And as explained earlier, as I was explaining earlier, that there are more powerful statistical tools available for continuous data. So we should prefer it over the discrete data set. Wherever possible, we should try to convert the discrete data set into a continuous one. Okay, so if we can go ahead and do that, if we have a choice, we should go ahead and do that. So let's try to explore some examples of discrete, and let's see, how we can convert that discrete into continuous data. For example, we talked about the you know, number of number of people appearing for the exam, right? So it can be so it is count. So how can we convert that count into a continuous data? So one of the way can be, I say, number of people appearing or appear for Six Sigma exam per month, right? So the moment I add a denominator, a continuous denominator, that data becomes a pseudo continuous data. You know, it's a different term. It is called pseudo continuous. It is not exactly continuous, but then you can treat it as a continuous data, right? So, and you know, concept wise, you know, the same definition that we use, anything that you can broke it down into finer refinements, but still you would be talking about the same thing. So number of people appear for Six Sigma exam per month, we can say per week, per day. It is, we are breaking it down, but still we are talking about number of people appearing for the exam, right? So we converted that discrete data into a continuous data, right? Number of calls received, you know, number of calls that I've received is a continuous count of calls, but number of calls received in a day, call per day, becomes a continuous data, right? Call per hour becomes a continuous data, call per minute becomes a continuous data, right? So depending on whatever discrete data that we have, we should always see if we can convert it into a continuous data and then you know, do the data analysis. Because only in continuous data you would be able to identify what is the measure of centering, what is the measure of dispersion, and you would be able to take action whether I need to shift the mean, I need to reduce the variation. You would not be able to do that in a discrete data set. Great. So let's move ahead. Okay, so they've given some indication um, of continuous discrete. So depending on the data type that you have, you know, you would calculate the capability accordingly. So in a continuous data, you would report Z long term, Z short term, or Z shift. So Z is basically, Z value is the sigma value of a process. For a discrete data, you would report defect Dpo, defect per opportunity, Dpmo, defect per million opportunity. So remember, if you just try and recall, we talked about a defect per million opportunity for a Six Sigma project. How many defect is there? You know, how many defect does a Six Sigma process produce? Very, very important. So we talked something on the lines of defect per million opportunity. How many defect per million opportunity would correspond to Six Sigma level? There cannot be any process whatsoever which has a zero defect. If there is any process which is reporting out zero defect, then there is some error in the measurement. Okay, we should always strive for a, see, Six Sigma is 3.4 defect per million opportunity. Okay, you increase the sigma level, it might be 2 defect per million. You increase it further, it might be 1 defect per million. You increase it further, it might be 1 defect per billion, per trillion, you know, per 100 trillion. But there would always be some defect. It cannot be ever free forever, right? But we should always strive to achieve a zero defect, but you know, practically it is not possible. To answer the question, 3.4 defect per million opportunity. All right, so I will move ahead and we'll go on to unit defect opportunity. So let's try to understand the operational definition of these. What is a unit? Unit is an item which is being produced. Defect is something which is failure to meet the customer requirement or the performance standard. The opportunity is any product service characteristic which is measured to a standard. What is defective? Any unit that has a defect is defective. And what does DPMO mean? Number of defects that would be there given a million opportunity. Okay, these are just a few terms. And then we'll talk about the data collection and we'll calculate the DPO, DPMO and all that. So some principle of data collection. See, in the measure phase, the first thing that you've done the your process mapping. After that, you would have identified certain areas as well. So you can put together a data collection plan to ensure that you collect all the data about all the data on the X's that you think are going to impact on the project Y. So you need to determine the objective of the data collection, identify the data type. So you would see whether it is a continuous data, discrete data, identify the control condition, decide the source of the data, what is the data that you need, what is the sample size that you would take. You put together the format of the data collection, put together the operational definition, everything, anything and everything that you can think of, so that there's no ambiguity in the data collection, because you would not do data collection every time. You would give it to resources who would do data collection for you. So you need to ensure that you capture as much information as possible to remove any ambiguity in the data collection. Okay. Now we come to sampling and population. So what exactly is sample? What do you think sample is?
A small set of the data.
So sample is a subset of the data. Yes, absolutely. So sample is something. Why do we do sample? Why do we do sampling? Why don't we take the data for the entire population? So, sampling, so collection of data cost money, right? So we might not realize it, but there are people who spend time, effort to collect the data. There are software whose maintenance, or the application whose maintenance fees is paid by the organization to collect the data, to capture the data, to maintain the data. There are servers required to store the data. So everything comes with a cost. Sampling is done to study a representative portion of the population. It is generally said that sample represent the population behavior. Why sampling is done? Why not population data? Because data costs money. If we were to collect the data for the entire population, it will cost huge amount of money and time as well. So that's the reason why we take representative sample from the population, and basis whatever we get from the sample, we interpret, or we infer the same for the population. So the term that describe the characteristics of sample is called statistics, and any term that describe the characteristics of population is called the parameter. Okay, so sampling is a process of selecting units from a population of interest by studying the sample, so that by studying the sample, we may fairly generalize our results back to the population from where they were chosen. So the task of sampling, as I was talking about, is undertaken because the information regarding a process or a product is not readily available. Okay, and the analysis of the whole population on which the critical information is needed is not feasible, and sometimes it is not possible as well. Okay, so that's the reason why we do sampling all the time. So there are few characteristics, of population, and this parameter is denoted by capital N, and sample size, which is statistics, is denoted by small n. And so the population mean or the sample mean is denoted by X bar or Y bar. Okay, it's not there. Otherwise, I've shown you that X bar or Y bar. We'll see that in the subsequent slides. And you know, and the reason, if you look at the overall, sampling, um, whenever we conduct a sampling, we want to be confident that the sample size is the representative of population. For that, there are various ways to conduct a sample, or because every time we sample, we conduct a sampling, there is a risk of bias, in the data. So in order to negate that bias, there are various techniques to pick up a sample. Also, statistically, we can find out how much is a statistical significant sample size of any given data set. So, some of the techniques or some of the approach to sampling, it can be broadly categorized into a probability or a non-probability sampling. Within probability sampling, it includes the random sampling, the systematic sampling, the stratified sampling, and in each of these each of these sampling, each item in the population has equal chance of being chosen in the sample. So for example, one of the example can be the customer satisfaction survey team picking the customer to be contacted and at random. So when it is random, there's a probability that anything can be chosen. And then there is something known as non-probability sampling as well, which is called non-random sampling or judgmental sampling. So where the members or the samples are selected from the population in some non-random manner. So the personal knowledge and opinion are used to identify the item for the samples. This can include, convenience sampling, judgment sampling, quota sampling, and there's something known as snowball sampling as well. So, for example, a forest ranger. So, in the subgroup sampling, that you see on that, it is one of the form of non-random sampling. So what happens is, for example, a forest ranger may decide to sample probably the northwestern area to cut the lumber, because he knows, he's using his subject matter expertise to do the sampling, and there might be some personal bias as well. So the advantage of probability sampling is that, for every sample that we collect, there is always a chance of error. Anything that we do, mathematically or statistically, there is always a chance of error. So the chances of error is called the sampling error. So the advantage of probability sampling is that the sampling error can be calculated. So sampling error is an error, is basically the degree to which a sample might differ from the population. Okay, so let's see, what is a random sampling? Random sampling is, each unit has the same chances of being selected. So you can either do it from a computer or write each unit on a piece of paper, deposit it in a box. And there are further ways of conducting random sampling. One is a simple random, wherein, you pick up anything, at random. Then there is a systematic sampling where you say every fifth, I would pick up every fifth item. It becomes a systematic sampling. And then there is a stratified sampling, wherein, it is kind of a superior method to random sampling. Stratum is a subset of a population that share at least one common characteristics. For example, male, female, or managers, non-managers. If you pick up from that particular subgroup, it is said that it is a much more structured way to calculate the sample size. So that's a bit about sample. Now, if I go ahead, there's some sampling approaches that has been given. Now, how do we calculate the correct sample size? Again, the calculation would depend on the kind of data that we have. If we have a continuous data, there's a different way of calculating sample size. If we have a continuous discrete data, there's a different way of calculating sample size. So I'm sorry for the misalignment that you see on your slide. Brittany, Charles, Nerlin, you're still there, right?
Yep, I'm here.
Yep.
All right. All right. So limitation of live online. You don't get to see the participants. So you need to check after some time. All right, so sample size for continuous data. So to calculate the sample size, we need to understand a few aspects or a few area. First, we need to understand, what is the confidence level. So confidence level is, is so for now you just understand, confidence level is how confident we want to be of the result. So generally, whenever or as a standard or typically we take 95% confidence level is generally taken if you are dealing with a process that includes, that has fatal errors or human lives involved. Then you would want to increase your confidence level to 99%. So they can be 95, 99 or 90% confidence level. And then with confidence, if you have 95% confidence level, that means it is equal to 0.05 of alpha risk. So what is alpha risk? Alpha risk is 1 minus 95% confidence. And alpha risk is calculated as 1 minus alpha divided by 2. So generally, whenever you have 95% confidence, then the alpha risk is equal, it is equal, 1 minus alpha risk is equal to 97.5%. So 97.5% of confidence, 95% confidence level, and the alpha risk or z-score of 97.5 will give us 1.96 as the value of z with 95% confidence level. We will understand how to look at the z table when we get into the analyze phase. For now, just remember, whenever you're calculating the sample size, and this just for your information, you have the sample size calculators available online as well. And I think you would be provided as well by Lecteron. In case if you need, I can send it to you directly as well. So you would have the calculators available wherein you would just need to put down the figures and it will calculate the statistically significant sample size for you. But this just for your information. If you have 95% CI or the level of confidence, then Z value that you would undertake to replace in the formula that you see is going to be 1.96. So the formula is, if you want to calculate n, small n is the sample size, which is Z which is 1.96 multiplied by the standard deviation divided by the value of A. A here is the acceptable defect rate. Okay, and you square everything, you will get a sample size. So if we calculate, if we convert the figures and if we calculate by assuming 0.15 as the value of standard deviation and 3% as the acceptable defect rate. So the equation would become 1.96 multiplied by 0.15 divided by 0.03 square of everything. So we will get a sample size of somewhere about 96 to 100, something like that. Okay, so some calculations on sample size and on the discrete data set. I again, just like you calculated for continuous, there is formula Z. Again, Z at 95% confidence level for discrete as well would be equal to 1.96. Okay, then you have P1 minus P. So P is a proportion defective, and 1 minus P, it's, so here it is 1 minus P. Generally, it is represented by Q as well. So the formula, it goes like Z square multiplied by P multiplied by 1 minus P. And then you divide the entire equation by the acceptable defect rate. So you will get a sample size for a discrete data set. Okay, I have a few examples, few calculations that I wanted to take you through to calculate the sample size. Are you okay going ahead with it, or do you want a quick 5-10 minutes breather and then we calculate sample size for couple of examples and then we move ahead, right? So let's quickly go through some of the examples of, some of the um, sample size questions. Okay, here we go. Let me know when you're able to see the slide which has sample size formula case study. All right, great. So here is a case study. So there's a farmer who packs rice in the bag for supplying all over the country. The weight of the bag with standard packaging is 10 kg with a standard deviation of 0.43. The farmer wants to conduct some study on the bags he supplies. He packs on an average 7,000 bags. So it is not possible to conduct study by checking all the bags. So he wants to calculate a statistically valid sample size. For farmer, the acceptable defect rate is 2%, right? So we need to calculate the sample size here. So now for us to calculate, first we need to see what is the information which is available to us. Uh, so what we're saying is that and because we have not been given the confidence confidence level, we'll assume it to be 95%. Okay, so when we say 95% confidence level, it is z would z is equal to 1.96 as we saw on the in the earlier slides. So acceptable defect rate, we have been given 2%, so the denominator is 0.02, and then we have been given the standard value of standard deviation, which is 0.43. So let me just quickly open the Excel and then input the values in the formula. So z is equal to 1.96. And then I have acceptable defect rate, which is 2% or 0.02, and then I have standard dev, which is I think 0.43, 0.43. So the formula was z multiplied by a divide the entire thing by a, or the acceptable defect rate raised to the power 2 square of this. This was the formula. So if we convert 1.96 multiplied by standard deviation divided by acceptable defect rate. So this is the value that we got. Okay, so the sample size that the farmer should calculate should be equal to 1776. I hope you're able to follow. I did not go too fast. All right. So this just for the concept to you. So as I mentioned, you would get a sample size calculator that you can use to calculate all this. You don't really need to do it manually. It's just that you should know as a green belt. Okay. So I will now go back. So for a discrete data set, how we go ahead and do that. Have you heard about Minitab? So Minitab is a statistical software that you would use when you work in Six Sigma, or especially when you go through the measure, analyze and improve phase. Especially analyze, because everything in analyze that we do would be on Minitab, almost everything. And then the topic that we will start tomorrow, which is measurement system analysis, that again would be on Minitab. So what I would request you to is to download Minitab. You will get a trial version which is available for 30 days free. So you can download Minitab 19. So whatever latest version that is available, you download that. I think the latest one is Minitab 19. All right, so that's regarding the sample size. I want to, so this is how the Minitab looks like. You have a session window, you have a worksheet window, and then, once I have Minitab older version on my machine, but then, it's, everything else remains the same. So what we'll do now, we will quickly go through um, some calculations on Dpo, Dpmo, so that we have we have that out of the way, and we know exactly how do we go ahead and calculate. So remember, for a continuous data, we would always calculate the sigma level or Z value or CP, CPK. For a discrete data, we would calculate Dpo, Dpmo, and all that. For a discrete data set, the calculation is fairly easy because all you need to do is you need to understand what exactly is the unit, what is the defect, what is the defect definition, what is the defect per unit, all those stuff. Okay, so in order for us to do the calculations on Dpo, Dpmo, there are a few areas that we need to understand, and we kind of discussed on that just a little while ago. We talked about what is a unit. So unit is what we are measuring. What is a defect? Defect is non-conformance. What is defective? So if there is a defect, the entire unit becomes defective. Okay. Then there is something known as opportunity for error. So what is the number of opportunity for error for every unit? So let's say, I am traveling and I'm going to the next city, right? And I'm going there by road. There are 10 red lights, 10 traffic signals in between. And how the defect is calculated is the number of traffic signals that are jumped. So there are 10 opportunity for error, during my, throughout my travel, because there are 10 red lights that I might jump or I can jump, right? So there are 10 opportunity for error. Okay. So let's say, I travel every day and every day I cross that city. So at the end of the week, 7 days, how many total number of opportunities I have? Every day I've got 10. So the total opportunity I would have 70, right? It is called TOP, or total opportunity for error. Okay, so these are the few terms that you need to understand, and then you should be able to calculate. Now, what we calculate, first one we calculate is called DPU, which is defect per unit. Okay, then we calculate, so first thing we calculate is total opportunity for error, then we calculate DPU, then we calculate DPO, which is defect per opportunity, and then we calculate DPMO, which is defect per million opportunity. Okay, now how we calculate defect per unit? Pretty simple. Defect upon unit, and this is defect upon opportunity, and then DPO multiplied by 1 million. Okay, we'll get the value.
Sorry to interrupt, but will we get copies of these examples?
Which examples?
Like the examples that you're doing here in Excel.
Oh, you will get the recording. So if you get the recording, you will get everything there because
Okay,
I have
got it.
saved everything that I've done.
Okay, great.
Okay, so these are the various things that you would calculate, and everything is there in the presentation as well. It's just that it is it is on different slides, right? So you calculate DPO by defect upon unit, DPO by defect upon opportunity, DPMO by DPO multiplied by 1 million. Okay, so let's go back to one of the case study. So there are 25 new hires join and are going through 3-day induction program. Their ABC bank salary account has to be opened within 15 working days, but for 6 new hires, opening of the account exceeded 15 days target. Okay, so what we need to do, we need to calculate. First, we need to identify what is a unit. So unit in this case is every new hire is a unit. Okay, so how many units are there at this example? So there are 25 units, and then there is an opportunity for error. So how many opportunities of error would be there per unit? See, what we are saying is, what is the defect? Whenever the opening of bank account for any of the hire takes more than 15 days or exceed 15 days target, then it is considered as defect. Okay, so how
Isn't it?
many opportunity per unit?
Is it 15?
No, 15 is the target, but
Is
defect
it
is
Oh, 6.
6? Yeah.
6. 6 is 6 are new hires whose opening exceeded 15 days target. So 6 is the number of defect, right? But the opportunity per unit. So what is opportunity per unit? So let's see again. Let's say there are 1, 2, 3. Sorry, 1, 2, 3, 4, 5. There are 5 new hires. Okay, so the defect, either the defect can be that account opened in within uh, within 15 days or beyond 15 days. Okay, so either it's going to be a defect or it's going to be not defect. Right. So what we are saying is, for every new hire, there's only one opportunity of error. Either is going to be either is going to be opened within 15 days or not. Right. There isn't any 2 or 3 opportunities. So for example, if we would have been looking at, let's say, in the same example that I took last time, where I'm traveling from one city to another city, and there are 10 red lights. Right. For every travel, there is 10 opportunity for defect because there are 10 red lights. For every red light jump is considered as a defect. Here, the defect is whether it is opened within 15 days or not. Right. So there is only one opportunity for error. You with me? Am I able to explain? Okay. So I'll go back to this. So how many opportunities for error per unit is there in this example? For every unit, there's only one opportunity for error. Right.
So
So whether
25.
it's successful, yeah, it's going to be successful or not successful. Okay. There cannot be any other option. Then what is a defect? Defect is any account that doesn't get opened within 15 days. So how many defects are there? 6 defects. 6 new hires, opening of account exceeded 15 days. Okay. So now, so if we want to calculate DPU, which is defect per unit, in this case, it will be 6, which is number of defect, divided by unit. Unit is 25. 6 by 25 would be the DPU value.
0.24.
0.24. So let's say 6 by 25.24. Then DPO would be same, because DPO is defect per opportunity. I mean, defect per opportunity, rather it is defect per total opportunity. Because the number of defect per unit is 1. So the total opportunity and the unit remains the same. So defect by total opportunity would again be 6 divided by 25. So DPMO is DPO multiplied by 1 million, which is 240,000 defect per million opportunity. Okay. Do you think it's a 6 sigma? This process is working at a 6 sigma level? What do you think? Is it close to 6 sigma, greater than 6 sigma, or less than 6 sigma?
Less than 6 sigma?
Way less than 6 sigma, absolutely. Because DPMO, defect per million opportunity, for a 6 sigma process, it should be equal to 3.4, right? It is 240,000, way high, right? So the sigma level should be pretty low. Okay, so is the calculation on defect, unit, DPMO, DPO clear? Okay, I'll take silence as no, so I'll need to take up another example. Let me just pick up this one. One second, I'll just flip the slides. Okay, so let's say we are in a manufacturing firm, and the firm manufacture air conditioner. Okay, and every air conditioner has got 4 parts. So it has compressor, it has condenser, it has fan, and it has coil, assuming these are the only 4 parts that it has. So air conditioner as a unit, what is the opportunity per unit? What do you think is the opportunity per unit? So for air conditioner to go wrong, either the compressor can be faulty, condenser can be faulty, fan can be faulty, or coil can be faulty, or more than one can be faulty. So for every unit, there are 4 opportunities for error.
Sorry to interrupt, but in terms of how long you're going to go for today, is there a time limit? Because at some point I am going to have to go.
No, just about 3 minutes, and then we're going to end. This is the last one that we had.
Okay, no problem.
Okay. So actually, I didn't realize that we have overshooted the time. So anyways, so let me just quickly complete this one. So 4 opportunities for error, right? And let's say we are auditing 10 air conditioners, and we found that 6 air conditioners are defective, right? Or there are 6 defects. So the DPU in this case would be 6 divided by 10 units that we are auditing, which is 60%. But DPO in this case would be different, because it's going to be 6 divided by total opportunity, which is 10 multiplied by 4, which is 0.15. So the moment the number of opportunities increases, opportunity for error increases, the DPO value would be way lesser than the DPU value. And then when you calculate 1 million, it will be 150,000 is the DPMO value. Okay, so this is how you would calculate DPU, DPO, and DPMO. So what we will do, we'll end the day today, and what we'll do tomorrow is when we come back, when we start tomorrow, we'll go through some of the concepts. We'll discuss, the information, the content that you would go through today after the training, and any question that you might have, we'll take it up tomorrow.
Yeah.
All right.
Have a
Thank
good
you
night.
very much.